Hello everyone, this is Sovik. Welcome to the video of important name reaction part 2. So we will start with the reaction named as Horner-Wadsworth-Emmons reaction. This is a reaction of an aldehyde. This aldehyde will convert it to the E-alkene in presence of N-butyl lithium as a base and phosphonate as a reagent. This is a phosphonate as a reagent. Now we'll see the mechanism. First, this N-butyl lithium will abstract the proton of phosphonate, and it will form anion, and this anion will delocalize to the carbonyl, and it will form this delocalized form. This is a delocalized form of the anion. This is delocalized form. Next step will be this negative, this anion will shift here, and this bond will attack on this bond, will make anion, and it will attack on this carbonyl carbon, and it will form a tetrahedral intermediate, which is a tetrahedral intermediate of this carbonyl carbon. Next, we have this O minus, so it will attack on this phosphorus, and this bond will shift here, so it will form a four-membered ring. So it will be 1, 2, 3, 4. Okay, so it forms to a four-membered ring. Next step, this is a very unstable intermediate, so it will cleave, this bond will cleave, and this bond will cleave like this, and it will form a E-alkene. Next, our next reaction is Hunziker reaction. In this reaction, it will convert the silver salt of this carboxylic acid to the alkyl bromide. This is alkyl bromide or alkyl halide, you can say, in presence of halogen and carbon tetrachloride as a solvent. Now we will see the mechanism. Mechanism follows the free radical mechanism. This is a free radical mechanism. So it will start with, like, this bond will cleave as a free radical mechanism, and this bond will cleave as a free radical mechanism, and this X radical here, from here we are getting like RCO O free radical plus silver free radical. Okay, next from here we are getting like silver 2 free XX halogen free radical. We will get this 2 will recombine, and it will form this silver halide, and these 2 will recombine, and it will form this intermediate. Next step, this bond will cleave, and it will form this free radical. Next step will be, this bond will cleave, and this will recombine to form CO2. Okay, and it will form as alkyl free radical, and in the system we have one halide free radical, so this halide free radical and this alkyl free radical will recombine to form alkyl halide. Our next reaction is Hosumi-Sakurai reaction. This is a Lewis acid catalyzed annihilation of various electrophiles like ketone, aldehydes, and imines and alpha beta unsaturated ketone, and acyl chloride also, and various other electrophiles with allyl trimethylsilane. This is allyl trimethylsilane. This will be common for all the reactions. This only this electrophiles will change in this reaction. So uh, here it will this allyl trimethylsilane will react with various electrophiles like ketone, aldehyde also, acyl chloride, alpha beta unsaturated ketone, and acetal, epoxides, imines, so many like electrophiles. So we will come in the mechanism of this reaction. So we will see the for epoxide mechanism. So in this reaction we are using Lewis acid as a catalyst. So epoxide will have a lone pair on the oxygen. So this lone pair will attack on the TiCl3, that is TiCl4, and removal of the it leads to the removal of the chloride ion. Next, it will form a bond of oxygen and titanium trichloride, and then next there will be two possibilities, like this bond will break, or this bond will break, or this bond will break. So we have two possibilities. If this bond will break, then it will form this species, which is a less stable species, and that is 2 degree 2 degree carbocation. This is a 2 degree carbocation, and if this will cleave, then it will form a more stable intermediate, that is a 3 degree carbocation. So it will be not possible, so this will be not possible. So this 3 degree carbocation in presence of in presence of allyl trimethylsilane, so what will happen, this double bond will attack on this carbocation. So it will form a carbocation carbonium ions here, followed by next we have a chloride ion in the system. So this chloride ion will attack on this trimethylsilane, and it leads to the removal of this trimethylsilyl chloride. Next we have this OTiCl3, and here will be double bond. Next, if we do hydration of this in the system, then it will form a unsaturated alcohol. So which is a major product. You can try this mechanism in case of both ketone, aldehydes, and other various electrophiles. The mechanism will be around same. So our next reaction is Joule olefination. It will convert, in this reaction it will convert this aldehyde or ketone to an E-alkene. Okay, Joule olefination always gives E-alkene. So how it will convert, like here aldehyde or ketone will react with a vinyl sulfonium carbanion, which is followed by reductive elimination with sodium amalgam solution. So now we will see the mechanism. So first this N-butyl lithium will act as a base. So this will abstract the proton of phenyl sulfonyl, alkyl phenyl sulfonyl, and it will form a anion, carbanion. This anion carbanion will attack on the ketone or aldehyde, and it will form a it will form a tetrahedral intermediate, which will be followed by H plus. It will abstract this, it will take H plus, so it will form this tetrahedral intermediate or hydroxyl sulfonium ion. Next it will next it will react with sodium acetate followed by acetic anhydride. So sodium acetate will abstract this proton, to form O minus, and this O minus will attack on the acetic anhydride. This is acetic anhydride, so it will attack on the carbonyl carbon of acetic anhydride, and it leads to the removal of acetate ion. So it will form OAC, that is acetate here, OAC, and here SO2PH. Okay. Next, when we will react with sodium amalgam and methanol, in presence of sodium and methanol, methanol and sodium will react like, and it will form sodium methoxide, which will act as a base plus H2. It will release one H2 gas. Okay, so this methoxide will be here. So this is a methoxide which will act as a base. So it will abstract this proton, and followed by it will remove this, abstract this proton, followed by this acetate will leave. So it will form a alkene. Next, it is like, now we can write this alkene like this. Next, sodium has one electron, like configuration of sodium is 3s2, 3s1. in this one we have one electron, so this electron will attack on the sulfur, and this bond will shift and it will form radical anion, and later this bond will break and it will form this hole will leave and it will form a radical. Now this radical and this electron from the sodium will recombine to form a radical, to form an anion, and this anion will abstract the proton from methanol to form an E-alkene. Okay. Our next reaction is Willsmeyer-Hack formylation. So it leads to the formylation of a electron-rich species, like electron-rich arenes. You can think like electron-rich species means like any phenol, and in aniline, like amine-based species, alkyl, or any methyl, alkyl, etc. These are all electron-rich species. So by reaction of this arene electron-rich species with a DMF and phosphonium chloride in presence of water, it will give para substituted product. Like this is a para substituted. This here hydrogen will be substituted with formyl group. Now in case of heteroaromatic species, this is a pyrrole. In these cases, this formylation happens in the two position. This is a furan. Here also this formylation happens in the second position. Now we will see the mechanism of this reaction. This is DMF. DMF1, in the DMF, nitrogen have lone pair. This lone pair will attack on the phosphorus, and this bond will delocalize, and it leads to the removal of the chloride. Next step, we have chloride in the system. So this chloride will attack on the carbon, and it leads to the removal of this whole phosphonium chloride and phosphorus. This species it will remove wholly. So and it will form this intermediate. Now we will now this arene will attack on this intermediate to form formylated product. Now this arene, this aniline, have nitrogen have lone pair, so it will push this lone pair. This bond will shift, and this bond will attack on the carbon, and this bond will shift, and it leads to the formation of this species. Now this there will be removal of this HCl. Okay, so it will form this species. Next, it will react. Next, we have H2O in the system, so H2O will react on this one. So this bond will break, and this bond will break, and this bond will break. So it will form NMe2 and here OH. Next, from here, like OH will be present like this, so it will be, this bond will break and this bond will break, so it will form, it will leave this amine NHMe2, and here it will form this paraformylated product or formyl, like aldehyde. Next, our next reaction is Prevost reaction. It allows the synthesis of anti-dihydroxylation of a alkene by addition of iodine followed by nucleophilic displacement with silver benzoate, and hydrolysis of the resulting diester leads to the antidiol. So here we are using alkene, so it will react with this. First it will react with this iodine, later it will react with this silver benzoate to form this antidiester. This antidiester will react with the water to form antidiol. So by Prevost reaction we can synthesize this antidiol. Only antidiol will be formed by this Prevost reaction. Now we will see the mechanism of the reaction. So for this alkene have double bond, so this double bond will attack on the iodine. This iodide ion will remove, and it will form this three-membered species, three-membered cationic species. Next, next will be like here silver benzoate will be present like silver plus and O minus. So O minus will attack on the on this one as a SN2A, like it will attack from the opposite side. So here you see O, CO, pH and I. Okay, next here will be NGP will happens like this. Oxygen have lone pairs. This lone pair will attack on this carbon, and it leads to the removal of the iodide. So it will form this five-membered species. And here again another equivalent of silver benzoate. Here silver benzoate is present as this silver plus and this benzoate ion minus. So it will attack on the SN2 pathway. So it will attack on this like this way, like it will attack from the opposite side of this like from, so that's why this bond will break, and it will form a diester type of anti-diester type of intermediate. After the hydroxylation, so if we do hydroxylation, so what will happen, this H2O will attack on the carbonyl, so it will leads to the removal of this, like breaking of this bond, and same this also. So it will form R CO OH, and here OH also. So it will form an antidiol here. Next is Woodward's dihydroxylation. In the Prevost dihydroxylation, in that cases alkene will be converted into antidiol, but in these cases alkene will be converted into a syndiol. So in this case we are using H2O in the reaction medium, so that's why it's giving antidiol. So in this case we are using silver acetate and iodide and H2O, and H2 as a protonating agent, and potassium hydroxide as a base. Now we will see the mechanism of the reaction. And so same, it will form a iodinium ion by breaking of this. So it will form iodide ion, and it is a iodinium ion. Later this will be present as silver plus and acetate ion, so it undergoes SN2 attack. So after SN2 attack, it will form like both iodide and acetate will be on opposite to each other. Later this will undergo NGP, and it leads to the removal of iodide. So it will form a 5-membered species. Later this H2O will attack on the 5-member species, so it will, this bond will break, and here OH will come. So it will, this bond will break, and this bond will break, so it will form OH, and here OSC. So in presence of acetate, the OCO, then like here acetate is present like this. Acetate is present like this. So this, in presence of H2O, this bond will break and it will form a OH. So it forms, at the end it forms syn diol. Our next reaction is Ullmann reaction. This is a copper 1 catalyzed nucleophilic aromatic substitution between the various nucleophiles and aryl halide. So here we are using aromatic like aryl halide and a nucleophilic species in presence of copper 1 catalyst and a base. It will it will undergo coupling reaction, and it will form a coupled products. In this case, the nucleophiles, like that reagent will be like some arenes, like amines, like alcohols, and any amines like NME2, no, NH2, Me, NH3 also, NH2Me, that is secondary amine, the primary amine, this secondary amine. This will be the this reagent. So now we will see the catalytic cycle. So in the catalytic cycle, will starting from copper halide 1 catalyst. So first this nucleophilic this reagent is present as nucleophile and bonded with H. Now if it will react with base, so base will abstract the proton, so it will abstract the proton, so it will form nucleophile minus. Okay, so when it will react with this when this nucleophile minus will attack on this, it leads to the removal of this halide. So there will be, at the end there will be removal of this hydrogen halide, and copper and nucleophilic bond will be there. Now in presence of aromatic like aryl halide, it undergoes oxidative addition. So in during the oxidative addition, this bond will break, and both will, this halide and this aromatic aryl species will be attached differently to the copper center, and due to this oxidative addition, there will copper will there will be increase in the oxidation state in the copper from +1 to +3. After this, it will undergoes reductive elimination, that is this and this will couple and it will remove from the system, so it will undergo reductive elimination. Due to the reductive elimination, the copper oxidation state of the copper will reduce from +3 to +1. So this way catalytic cycle will goes on and on. Next reaction is Tishenko reaction. This is a preparation of an ester by using two equivalents of aldehyde and aluminum alkoxide. Okay, so it will form a ester. So now we will see the mechanism. Mechanism started with aldehyde. Oxygen have one lone pair, so this lone pair will attack on the aluminum alkoxide, and it removes this alkoxide, and it will form this bond, like oxygen aluminum bond. Later this bond, so this is a more electrophilic center, so this bond will break. This bond will break, like this will be negative, delta negative, this will be delta positive. So if it will be minus, this will be plus. So minus will attack on this one, and this bond will break, and it will form O, and here it will form C, each R plus positive, like here cation will form. So after this, it undergoes this hydride shift, like one in the system we have this alkoxide ion, so it will attack on this aluminum, and this bond will break, and it will form here ketone, and this bond will break, so it will form hydride, and this hydride will attack on this cation to form this ester. So this is a 1,3 shift, 1,3 hydrogen shift, because this is 1, 2, 3. Hydrogen is going from 1 to 3 position. That's why it is 1,3 hydrogen shift. Next is Luce reduction. Luce reduction is like, in case this is a special type of reduction by using the sodium borohydride reagent. So in case of 1,2 enone, like alpha beta unsaturated, this is a alpha beta unsaturated ketone. So in the normal condition, like normal reduction, in normal reduction will be sodium, we are using sodium borohydride and methanol only, so it will reduce it will reduce this alkene selectively. But in case if we are using cerium chloride as a catalyst, so it will reduce this ketone selectively other than this double bond. Now we'll see the reason, like what is the mechanism, what is the reason behind this. So sodium borohydride, in presence of 3 molecule of methanol, it will form this NaBH OMer whole thrice plus 3H2. So it becomes, in presence of cerium chloride only, this it forms this complex. So it will be a very hard donor. So this hard donor will donate one hydride ion, and like in a HSAB principle, hard donor will hard combination will be more preferred than hard soft. So here this center is more hard, and this hydride ion also hard donor, so it will attack on the ketone, so it will form a like alpha beta unsaturated alcohol, so it will be a 1,2 reduction. So it will be 1,2 reduction. Next, Our next reaction is manic reaction. It leads to the formation of a alpha methylated amine of an enolizable carbonyl compound. This is a enolizable carbonyl compound by a multi-component reaction of 1 degree or 2 degree amine with formaldehyde and enolizable carbonyl compound. Here this is formaldehyde we are using, and amine, that is 1 degree and 2 degree. This is 2 degree amine. It, and after this reaction it forms alpha. This is the alpha, and that is alpha methylated, that this is methyl, that's why methylated amine. Now comes to the mechanism. First mechanism starts with this formaldehyde is a reactive species, so it will be at this carbonyl will be so much reactive, so this lone pair of the amine will attack on the aldehyde, and it leads to the delocalization of this bond to this O, and it leads to the formation of CHO minus and NH R double dash plus. Now this position, this O minus will take this H plus, and this bond will break, and it leads to the formation of this intermediate. Next step, there will be like this lone pair will delocalize, and it leads to the removal of this OH minus, and it leads to the formation of a imine. This is a, no, not imine, this is a iminium ion, and it leads to the formation of a iminium ion. Now we have a enolizable carbonyl compound. So this carbonyl compound will enolize to form a enol form. After this, this bond will be, this lone pair will attack, will shift like this, and this bond will break, and it will attack on the carbon atom of the imine, and this bond will delocalize like this, and it will form R, and it will form R here, CH2 NR2 double dash R dash here O H plus. Next step, there will be removal of this proton ion, so it leads to the formation of alpha methylated amine. Our next reaction is Mukayama aldol reaction. As we know, the aldol reaction is two aldol, like two aldehyde will combine. Like if we take two acetaldehyde, will undergo self reaction in presence of base, so it will give this product, this aldol product, condensed aldol product. This will, it will give this product. Okay, now in this reaction, like this is also a aldol reaction, but in this one, its reaction will be catalyzed by a by a Lewis acid, that is a titanium catalyst or any other Lewis acid catalyst, and this reaction is going by this silyl enol ether enolate. This is a silyl enol ether. Okay, so let's see the mechanism. This now first it will this we have this ketone, so we have LDA, that is lithium diisopropyl, that is diisopropyl amide. So it will abstract this proton and it leads to the formation of a lithium enolate. Here it will abstract this lithium, so it will form lithium enolate, and here double bond will form. So this is a lithium enolate. Next step is this will be present as plus minus, oxygen minus and plus. If we react this with TMS chloride, that is trimethyl chloride, so this negative charge will attack on this is trimethyl group, and it leads to the removal of this chloride, and it leads to the formation of TMS, OTMS, which is a silyl enolithiol. Now as we, and at the other hand, like we have one aldehyde. Okay, so it will attack this T. So this it will react with this. It will react with this Lewis acid, TiCl4, titanium chloride. This lone pair will attack on the titanium, and it leads to the removal of the chloride. And it leads to the formation of this cationic species. Okay, so this is the this species. So now what will happen? This is a cationic species, and this is a electrophilic. This is a electrophilic species. So here lone pair will so this is a much more nucleophilic species than this, so this will attack this lone pair will delocalize here, and this bond will break and it will attack on this carbonyl center, and there will be shift of this bond, so it leads to like RCO. Here will plus will come, and CO TiCl3 R dash. Next step will be like as we see this now we have chloride in the system, so chloride will come here and it will attack on this one, and it leads to the removal of this bond, and another chloride is there, it will also attack on this, and it leads to the removal of this bond, and like breaking of this bond, and it will form like RCO, and then R, then O minus and R dash. Then there will be protonation, and it leads to the formation of this product, that is this aldol product. So this is the aldol product. Next reaction is Mitsunobu reaction. This is a nucleophilic substitution of a 1 degree or 2 degree alcohol in presence of dead. Dead means diethyl azo dicarboxylate, and diad means diisopropyl azo dicarboxylate, and triphenyl phosphine. So this is in present in case of 2 degree, in case of 1 degree alcohol, there will be no like it will convert to, there will be only nucleophilic substitution will happen, but in case of 2 degree alcohol, there will be inversion of configuration will happen. In this case, here nucleophiles will be like alcohols, carboxylic acid and azide. Now we will see the mechanism of this reaction. So this is a dead means diethyl, like diethyl means this diethyl, this 2 ethyl diethyl azo, this is azo, this is azo and dicarboxylate. This is the two carboxylates. That's why diethyl azo dicarboxylate. Now we have triphenyl phosphine in reaction. So triphenyl phosphine reacts, it will attack on this dead nitrogen, and there will be shift of this double bond, and it will form this intermediate. Now it is a nucleophilic species, or it will acting as a base, so it will abstract the proton which is associated with the nucleophile. So now it will form a nucleophile, that is minus. Now after this it will form this intermediate. Now we have this alcohol, this 2-degree alcohol. So it will attack on the lone pair of the on this hydroxyl ion. It will attack on this species, and it leads to the breaking of this bond, and it leads to the formation of this O pph3, O plus pph3. And after this we have nucleophile. As you see, we have nucleophile minus. If we have, so it will react on, it will attack as a SN2. It will undergo SN2 attack. So there will be shifting of this bond, like not shifting, it will there will be removal of this bond, and it leads to the formation of this uh, a substituted product which has inversion of configuration. Now we will see the three defined type of nucleophiles. One is alcohol. If we use this alcohol, it will give the there will be nucleophile minus will be this. This is minus, this is plus. So it will attack. So it will form this ether in presence of this carboxylic acid. It will form this carboxylate or ester, you can say. And in presence of this hydrazoic acid, that is HN3, this one, it will give azide. So this is azide, this is ether, and this is ester. Our next reaction is Nazarov cyclization. It allows the synthesis of a cyclopentadiene from divinyl ketone, from divinyl. This is 2-vinyl and this is ketone, catalyzed by Lewis acid. We can use any various Lewis acid like aluminum fluoride, BF3, TiCl4, etc. This Lewis acid catalyst. So this will cyclize, and it will form this cyclopentadiene, and this divinyl ketone will cyclize to form this cyclopentadiene. Now we will see the mechanism. Here first it will start with like divinyl ketone. We have AlCl2, AlCl3. So lone pair of this divinyl ketone attack on this AlCl3, and it leads to the removal of this chloride ion, and it leads to the formation of this bond, of this intermediate. Next, now there will be two type of shifting. One is this bond will shift here and this bond will shift here, and there will be another type of shifting, like this bond will shift here or this bond will shift here. So there will be two type of intermediate will form, like possible intermediate. Like here you see, because of this, if it will shift, if this will shift, then it will this cation will form. If this bond will shift, then this cation will form. But in this case, you see this is a 3-degree carbocation, which is a more stable than the 2-degree carbocation. So this is this carbocation, like this this product will be form minor, or else it will be not possible. So we will go forward with this carbocation. So after this, it will cyclize like this, bond will shift here, and it will cyclize like this, and positive charge will come here. So it will form positive charge here. Okay, next, next we have chloride ion in the system. So chloride ion will attack on this uh, AlCl2. So it leads to the removal of this, breaking of this bond, and breaking of this bond, and it leads to the it will abstract this proton from the system, and it will form this species. After this, there will be removal of the abstraction of this proton from this compound, and it leads to the formation of cyclopentadiene species. Next is NEF reaction. Uh, this is a conversion of a nitro compound into a carbonyl compound, which is catalyzed by using base and acid. Okay, so this is a nitro compound which is in presence of base and acid. It leads to the formation of a ketone, or any like if it is a ketone or aldehyde, it will be formed. Now we will see the mechanism of this reaction. So it will starts with nitro compound. Here sodium hydroxide will acting as a base, so it will abstract the proton. So this proton will abstract, and this bond will break, and this bond will come shifts like this, and this bond will shifts like this. Again, in presence of acid, this anion will abstract this proton from the system, so it will form OH. After this, we have H2O. So H2O will attack on the carbon, this carbon, and this bond will shift, and it will form like OH. So it will form like R dash. Here it will be OH2 plus, and O minus. Now in the next step, it will abstract this proton, and this bond will break, and it leads to the formation of this intermediate. After this, there will be removal of this removal of this bond, like there will be breaking of the CN bond, and it leads to the formation of this ketone or aldehyde. If R dash is H, then it forms aldehyde. Next reaction is Ritter reaction, and this is a acid catalyzed nucleophilic addition of an acid catalyzed nucleophilic addition of a nitrile to a carbonium ion, which is formed from the alkene or alcohol, followed by hydrolysis to give an amide. Okay, now we will see the mechanism. So we are using we can generate a carbonium ion via two process, like via two ways. We can use this alkene or this alcohol by using in the acid catalyzed system. So in presence of acid, its bond, the alkene will abstract this H plus from the system, so it will form this carbocation. And in presence of in case of alcohol, it will abstract, it will it will abstract this proton from the system, and it leads to the formation of a OH2 plus. After this, there will be removal of H2O, so it will form this carbonium ion. Next step, we have nitrile ion, nitrile in the system as a reagent. So nitrile have nitrogen have lone pair on its orbital. So this lone pair will attack on the carbonium carbocation. So there will be plus charge will come in the nitrogen. Now now we are doing a hydrolysis. So in the hydrolysis, H2O will attack on the carbon and they will be shifting on this to the nitrogen. So it will form like R C OH2 plus double bond in this. Okay. Next step, there will be the removal of this H plus and it leads to the formation of this intermediate. Next step, there will be like tautomerization, like uh, it will tautomerize to the amide, so it will form amide. In case of this alcohol, it will form this type of amide in presence of this nitrile uh, and in presence of this formic acid as a acid which is acting as a catalyst in this reaction. Our next reaction is Reformatsky reaction. Addition of this is a addition of a carbonyl compound with stabilized organozinc reagents. Like this, there like there if carbonyl compound will be there, then if any other nucleophile is there, then it will attack and it leads to the formation of the and it leads to the formation of this tetrahedral intermediate, and this attack is called as 1,2 addition. Now in this case, this bromide species will form zinc bromide, that is a organozinc compound in presence of zinc, and that organozinc compound will undergo 1,2 addition with this ketone or carbonyl compound, and it leads to the formation of this compound. Now we will see the mechanism. In presence of zinc, and this this bromide compound will undergoes alpha brom. This is a alpha bromo ester. This alpha bromo ester undergoes reaction with this zinc in toluene, and it gives this organozinc compound. And in presence of and this organozinc compound will react with this carbonyl compound by this 1,2 attack, and it will form this OZNBr. And in presence of like if we are doing any acid workup, then it will give this hydroxyl here and ester. Next is Rosenmund reduction. This is a catalytic hydrogenation of a acyl chloride, which leads to the formation of aldehyde. This is acyl chloride. In presence of this catalyst, that is palladium and barium sulfate, it undergoes reduction to aldehyde. Our next reaction is Robinson annihilation. In this reaction, it leads to the formation of a cyclohexene derivative like cyclohexenone, derivative by reaction with a carbonyl compound with alpha beta unsaturated compound in presence of this base. Now we will see the mechanism of this reaction. First, this potassium hydroxide will abstract this proton, because this proton is much more acidic than this proton. Because if after abstraction this proton of this proton, it will form a negative charge here, so it will be stabilized by this aromatic system. But if this proton will be abstracted here, if we put one anion, but this anion will not stabilize by any aromatic systems or any delocalized, or it will be not stabilized by any other systems. So these protons will undergo like abstraction. So this proton will abstract and it will form enolate, and this enolate undergoes Michael addition with this alpha beta unsaturated carbonyl carbon, which is known as 1,4 addition. So it will form this CC bond after abstraction the H plus from the system. It will form enol, and enol will tautomerize to the ketone, this ketone. Now in presence of another equivalence of uh, this base, it will abstract this proton and it leads to the formation of this enolate ion. So this enolate undergoes cyclization by after attacking on this carbonyl carbon, and it will form a six-membered ring after and this O minus will abstract the proton from the system, and it will form the aldol product and in presence of another equivalent of base, it will abstract this proton and it leads to the removal of the OH minus. That is, overall it will remove this H2O and it leads to the formation of this cyclohexenone derivative. Okay. Next is Sandmeyer reaction. It is a substitution reaction of a aromatic amino species to the aromatic halide via this diazotization and via diazotization. So here in aniline, here you see aniline will react with sodium nitrite in HCl. So how it will react? So nitrite will present in this form. So it will present like O minus, and this it will present like this. In presence of H plus, that is HCl, we are using acid. So it will this proton, it will abstract this proton. So it will form NO. In presence of another equivalence of acid, it will abstract this H plus and it will form H2O plus, and in double bond O, here it leads to the removal of this H2O and it will form nitrosonium ion. This is a nitrosonium ion, and this nitrosonium ion will be attacked. This is an electrophilic species. So this nitrosonium ion will attack by this aniline, it will attack on the nitrogen and this bond will break. It leads to the formation of NH double bond is NH double bond N double bond NO. No, like it will form single bond in double bond O. In presence of base, no, in presence of acid, it will abstract this proton and it will form which here plus. Next, it will after this in this bond will break and this bond will break and it leads to the removal of the H2O and it leads to the formation of the diazobenzene. In the system we have HCl, that's why it combines to form this azide chloride into Cl. So from here, if in presence of copper halide, it undergoes like it will be present in plus and minus. Here it undergoes substitution and removal of is nitrogen. So it will give halide. Our next reaction is Sharpless asymmetric epoxidation. As we know, we know the epoxidation of a alkene. We can do epoxidation of a alkene by using the MCPB or any other par acid like HCO3H, like H2O2, but this will give a diazo selective product but not enantiomer selective. Like we are not getting a single enantiomer, so we are not getting we are not getting any we are not getting any E from these reactions. We are not getting any E from this reaction. So by using this Sharpless epoxidation, we can convert the allylic alcohol to the by reaction with tert butyl hydroperoxide, which is a epoxidizing agent. This is a epoxidizing agent. This is a epoxidizing agent and chiral diethyl tartarate as which is catalyzed by, and this reaction is catalyzed by titanium tetra isopropoxide catalyst. So this we need titanium we need allyl alcohol in presence of titanium tetra isopropoxide and plus in presence of plus TET. This is and tert butyl hydropropoxide and DCM. It will give this particularly this hydroxide, like this epoxide, which is a chiral, and in presence of minus TET, it's giving this chiral epoxide. So both are chiral. So both are optically active species. Now there is a trick to remember how to get these products. Like when we are changing this plus D, this DET, this chiral space, this is acting as a chiral ligand. So in presence of this chiral ligands, there will be change in the stereochemistry, like from which side this epoxidation will happen. So that will be decided. Now we will see the trick of these reactions. This is a allylic alcohol. This is a simple allylic alcohol. So you see, now we need to this is H and this is CH2OH. Okay, so we need to make it straight, like in a perpendicular. When you are making perpendicular this double bond, so CH2 coming this side and H coming this side. Now you see CH2OH is coming on the right side. So if we are using plus DET ligand, now then this epoxidation will happens from the wedge side, like it will comes our above the plane. So epoxidation will happen above the plane, but in presence of minus DET it will happens below the plane, that is dash position. In presence and in case, and in this one you see, in this case you, this is first case, this is second. In this one, if we are making this, if you are if you are making this one to top particle, that is CH2 is to top particle, so CH2 is coming to the left side. So when CH2 is coming to the left side, then it will be reversed. So in presence of plus DET ligand, epoxidation will happens from the dashed position, and minus, in presence of minus DET, epoxidation will happens from the wedge position. Now in this case you see, this is a Z alkene and this is a E alkene. This is a Z alkene. Now we need to make this CH2H to the top vertical. Okay, when we are making this to top vertical, you see this CH2OH on the is present on the is present on this right side. So here you see CH2 is right side, means if we are using plus DET ligand, then epoxidation will happen from the wedge side. If we are using minus DET ligand, then it will then epoxidation will happen from the dashed position, that is it will form like this in presence of this minus DET. Okay, in presence of minus DET it will form like the epoxidation will happens from the dashed position, like below the plane. Now we will see the sharpless asymmetric hydroxy dihydroxylation. As we know, like by using OSO4, it will give a syn hydroxylation, like this it will undergo syn hydroxylation, but it will give both, it can give it will give both isomer, like so this is not a, so these reactions are not a, in a enantioselective selective, so we are getting E around to be 0. So by using this strategy, like sharpless asymmetric dihydroxylation, we are getting particularly that chiral diol only, syn diol. This is a chiral and this is also a chiral. So what is happening in these reactions, like here you see this is acting as a like a dihydroxylation agent, like K2OSO4, and it will be converted to OSO4. And this potassium ferrocyanide, this is a potassium ferrocyanide which is acting as a oxidizing agent. So here potassium ferrocyanide will oxidize this OSO4 after the, like after reactions with this first OSO4 present in OS8. OS8 after reactions with after reactions it converted to OH6. So in presence of potassium ferrocyanide, it will convert this OH6 to OH8 again. So in that way we can use this reagent as a catalytic amount only. No need to use this as a reagent as a reagent. So this will be because this will acting as a oxidizing agent. Next we are using this DHQ, that is a dihydroquinone based. This is a dihydroquinone. This is a dihydroquinone based ligand. In presence of this dihydroquinone based ligand, dihydroxylation will happens mostly from below the plane only. Like it will happens from the dashed position, like below the plane. But in presence of the DHQD, we are using another type of chiral ligand like dihydroquinidine. Here here this seen dihydroxylation will happens from particularly from the wedge side, that is above the plane. Only above the plane this dihydroxylation will happens. So it will also give a chiral species. So this is a trick. Okay. Now Steter reaction. This is our next reaction is Steter reaction. This is a 1,4 addition of an aldehyde to an alpha beta unsaturated compound. This is alpha beta unsaturated compound, which is catalyzed by cyanide. In presence of DMF, it will form condensed like CC bond, CC, and it will form a CC bond. So now we'll see the reaction mechanism of these reactions. So first, this sodium cyanide will attack on the cyanide ion will attack on the carbon, and this bond will shifts. After this my O minus, that is this O minus will abstract this proton, and it leads to the formation of this stabilized carbocation. No, carbanion. After this stabilized carbanion will undergoes attack on this 1,4 attack, that is Michael addition. One-four addition to this alpha beta unsaturated carbonyl carbon, and it leads to the formation of this CC bond. Now this it forms a anion, and this anion will abstract this proton, and this after abstraction this bond will will broke, and this bond will broke. So it leads to the removal of cyanide ion, and it leads to the formation of our CC bond link, that is a condensed proton. Next, our next reaction is Kim-Schmidt reaction. This is a acid catalyzed reaction between the hydrazoic acid with various electrophiles such as carboxylic acid, aldehyde, ketone, alcohols, and alkene in presence of this hydrazoic acid. And acid, we are using acid as a, that is H2SO4 as a acid, as acidic conditions. So we will see the mechanism of these reactions. So first it will react like hydrazoic acid will present like this in this form. So it can present in this form also, like this this minus will delocalize and this bond will broke, and so minus charge will come on this nitrogen. Now we will see this is a HN3, that is hydrozoic acid. This is a point. So this, in case of carboxylic acid, this anion will attack on this carbonyl carbon, so it leads to the formation of this O minus, and then this O minus will come here, will come minus charge will come back here, and this bond will break and it will shift to this nitrogen, and it leads to the removal of this nitrogen. So it leads to the formation of this RNHCO2H, which is a type of amide. Now if we are heating, so in present if we are heating, there will be removal of this CO2. So if it is CO2 will remove, so it leads to the formation of amine. Now in case of aldehyde, this minus charge will attack on the carbonyl carbon, and it leads to the formation of O minus. Next step, like this minus will come here, and this will attack on this R bond, will shift from carbon to the nitrogen, and there will be removal of this nitrogen gas, and so it will form a carbamide. Next, in case of ketone, this it will attack on the carbonyl carbon, and it leads to the formation of this intermediate. Next, this minus will come back, and there it leads to the removal, like there will be shifting of this alkyl group from carbon to nitrogen, and it leads to the removal of this nitrogen. So it leads to the formation of this amide, like amide. In case of H2O, like in case of alcohol, so this this OH this hydroxyl will abstract this proton from the system, so it leads to the formation of H2O plus this cation, and later it will have next this minus will attack on this carbon, because this carbon is electrophilic center, and it leads to the removal of this H2O, so it will form this intermediate. Now there will be removal of this nitrogen, followed by 1,2 shifts, which is on there, like alkyl group will shift from carbon to the nitrogen, which is known as carbon shift, 1,2 shift. So it will form this carbanion, no, carbocation. Later it will abstract this proton, like this proton will be abstracted, and it will form this imine. Next we have alkene. In the same alkene, now alkene will abstract the proton from the acid, so it will form this carbonium ion, and this carbon in this carbonium ion, this minus charge of this HN3, that is hydrozoic acid, will attack, and it will form this intermediate. There will be removal of this N2, so it will form this this type of intermediate. So after this, this alkyl group will shift from carbon to the nitrogen, which is known as car 1,2 shifts, which will be which will which will know which will be known as 1,2 shift. After this, this proton will it will abstract the proton, so it will form not this proton, like this proton, it will abstract this proton, so it will form a type of imine. So our next reaction is Peterson olefination. This is a reaction of an aldehyde or ketone with an alpha silyl carbanion followed by acid catalyzed or base catalyzed elimination, which leads to the alkene. So our main product will be alkene from aldehyde or ketones. So this okay. So this base, in presence of base, it will abstract the proton from silyl carbon, and it leads to the formation of alpha silyl carbanion. And this alpha silyl carbanion will attack on the carbonyl carbon and will shifts to it will form a bond like CC bond. So it will form now this there will be two diastereomer will be formed, like one in one case like where over hydroxyl which is formed by attack on this carbonyl carbon, and hydroxyl ion hydroxyl and this TMS group will be on the same plane, and another case where both are in the opposite plane. Now if we are using acid catalyzed, that is BF3 ET2O. Now in this case, in case of acid catalyzed reaction, it undergoes anti-elimination, that is both hydroxyl and this SiMe3 both should be anti, then only when this elimination will happen. And in case of base catalyzed reaction, this acid should be anti and base will be syn. In case of base catalyzed reaction, this both SiMe3 TMS and this hydroxyl group should be in syn to each other, then only elimination will happen. So now we will see the mechanism of these reactions. So after this for this isomer, like for this diastereomer, if it will react with this under this acid catalyzed reaction, so this it will here hydroxyl group have lone pair of electrons, so it will abstract the, so it will attack on the BF3 Lewis acid, and it will form this intermediate. Next, like now this you see this this OBF3 and SiMe3 is seen to each other, but in under the acid catalyzed reaction both should be anti, but in this case it's syn. So we need to make changes in the conformation. So first we need to convert this conformation into the Newman projection. So where you see this R and R dash are in the trans to each other, and this SiMe3 and OBF3 will be into each other. Here SiMe3 and OBF3 is seen to each other. Now we need to do 120-degree anti-clockwise rotation. So after 120-degree anti-clockwise rotation, this will shifted to here, this hydrogen will shifted to here, and this R dash will shifted to here. So R dash will be here, and here you see this R and R dash is are now in seen to each other, and this SiMe3 and OBF3 will be anti to each other. So here you see both SiMe3 and OBF3 are anti to each other. Now in this case, elimination will be possible, that is anti-elimination, and it leads to the formation of this Z alkene because this R and R dash are seen to each other. Now I'll come to the next isomer, like another like same isomer. If we are doing base catalyzed reaction, in base catalyzed reaction elimination should be seen. So here you see both hydroxyl and SiMe3, that is TMS, are seen to each other. So under this base catalyzed reaction, this hydride will abstract this hydroxyl hydrogen, and it will abstract this proton. So it will form this O minus, this intermediate. Now we will write this intermediate like this, like this R and R dash are in both R and R dash in opposite to each other. So this is above the plane and this is R dash is below the plane, and now this O minus and SiMe3 are in the same plane. So this is same plane, so it is showing like both are in same plane. Now it will form a bond with this TMS. Next step, there will be scene elimination will happen. This bond will break and this bond will break. So it will form a E alkene because here both R and R dash are in anti position. So it will form a E alkene. Now I will come in the next isomer, that is trans isomer, where both where TMS and this hydroxyl group are in different in opposite, like both TMS and this hydroxyl are in opposite direction, like opposite plane, like this is above the plane, this is below the plane. Now in presence of hydride, that is base catalyzed reaction, it will abstract this proton and it will form this O minus. Now you see both O minus and SiMe3 are anti to each other, but we need to make this to seen. So now we need to change the conformation, like we need to convert this conformation to the Newman projection. Here you see both both R and R dash are in anti to each other, and O minus and SiMe3, that is TMS, are anti to each other. Okay, now we need to do 120-degree rotation, clockwise rotation. So if we are doing 120-degree clockwise rotation, this will come here, this will go here, and this will go here. This R dash will go here, O minus will go here, and H will come here. So H will come here. See, but now you see both O minus and TMS are in the same, like are seen to each other, and R dash are seen to each other. So here we can convert this to this conformation, like both R and R dash in same plane, and this TMS and O minus will be in the same plane. So it will form a bond with this silicon, like TMS, and later it will undergoes a trans scene elimination. So it will form a Z alkene. Now in this case, it will after in this case this is a acid catalyzed reactions. So it will react this hydroxyl and will attack on this BF3. So it will form this intermediate. After this, you see, like in acid catalyzed reaction, both this OH and TMS should be anti, and here both are in anti, so we don't need to do anything. So it will undergoes elimination. So it will give a E alkene because here R and R dash are in are anti to each other. This is the last reactions. It is Simon-Smith cyclopropanation. This is a reaction of an alkene with with a diiodomethane in presence of zinc copper couple. It leads to the formation of cyclopropyl derivative. This is a cyclopropyl derivative in presence of diiodomethane. It leads to the cyclopropyl derivative. Now we will see the mechanism of these reactions. This is diiodomethane. So in presence of zinc, this will zinc have lone pair on this on its orbital, so it will abstract it will attack on this iodine, and then this it will form this bond will break and it will attack on this zinc, so it will form iodine CH2 ZnI. Next, like it will this bond will break, and this bond will break and it will combine with ZnI2. So there will be removal of the zinc iodide, and it leads to the formation of CH2 carbene. This is a triplet carbene. As you know, the triplet carbene is the sp2 carbon. In sp2 carbon, this both it have two electrons, and both electrons are in parallel spins, so that's why it's a triplet carbene. Now this carbene now this carbene will attack on this electron, like alkene, and this alkene will attack on this carbene carbon, and it leads to the formation of this cyclopropyl derivative. Now there is a special case, like if there is any hydroxyl group in the in the system, then that cyclopropionation will happens from the same side, like cyclopropionation happens from the same face of hydroxyl group. Like if if hydroxyl group is present on the above the plane, then cyclopropionation will happens from above the plane. If hydroxyl group is present below the plane, then cyclopropionation will happens from below the plane. Okay. If you find this video helpful, then please like this video and subscribe this channel and share with your friends. Thank you.